Never had to use one of these, so. Okay, my name is Devine. I've been with the McNair program for 3 semesters, and you can read a little bit more about me in the flyer. And my advisor, Professor Michael Minotti. I'm covering a topic that's not necessarily common in statistics, and it's kernel density estimation. So in any real experiment, a problem arises that we would like to be able to describe and depict our data in the best fashion that we can. And often enough, that means describing the mean, median, and modes of a distribution, and potentially anti-modes, where we have valleys in our graphs. And doing so allows us to actually show what the actual distribution that our data is coming from, and how we can, just being able to describe that's very valuable, because then we can potentially describe other features, other things we can extrapolate from that. This is actually my old PowerPoint, just to point that out. Yeah, I sent another one the day you said it was due, but anyways, it's just there's better graphs. Okay, so the best way to depict this is with a histogram, common enough. That's the more elementary depiction of what I'm describing. And with a histogram, you can describe essentially where the modes are at. You know, if you have a normal distribution, using a histogram would show along each subinterval that you have describing your graph, data accumulated to describe the height of it, and then each, for example, a normal distribution, you would have a very good depiction of what it actually looks like along the tails and the center of it. And so here we would describe that as using the bins. Now, having bin widths is a very, very identifying thing to actually have in a histogram, for example, because you can have accumulated observations along each subinterval, and accounting those, that's where you get the height of the histogram's bar. And so we have 2 cases, discrete and continuous. The histogram covers the discrete case, essentially, because it's not a flowing graph as you would think of with the actual normal distribution, for example. And that's then that goes to the next part, which is representing with the histogram potential experiment. And so in this case, we have, for the observations along our x-axis, we count the number of the ones, or we count how high it is essentially with each box. And so this is the range, and then this is each subinterval. And then along each subinterval, we count the number of observations, we stack them, and then this overall feature that we describe is essentially skewedness to the left. And so that's the feature of this particular distribution. Now, because we can choose our bin width and we can potentially shift it, that means we can actually change, instead of starting at roughly 2, we go to, say, 1.75. Well, shifting back our bin width creates this gap in the data. We see it here, but because it encompasses some observations, we can actually depict it. But here again, we are missing an entire bin width. And so this distribution does not look anything like that. And so what we're being able to describe is that choosing a bin width actually chooses how we can represent our graph. And knowing that allows us to say a common idea with the kernel density estimation, that if we have this function, a kernel, this is how you represent it, that we can describe a similar feature, which would be the bandwidth. Likewise, the bandwidth describes the histogram's smoothness, but for the kernel. And so what would that look like? Well, just as we have a tiny box for each observation in a histogram, we have a kernel to represent each observation in a continuous fashion in a non-parametric method. So here we show 1 kernel, and then 2 kernels you can see accumulates the actual density below it. And so that means where there is less data, we can show that there is still a potential to get data. Going back, if we look at our graph here, the common problem that we have then is that we aren't describing with this depiction the potential of getting data there. And that's not necessarily the case in an experiment. We could actually just have not gotten data there because we took a low sample. And so, likewise, you can see that more kernels allows for more accumulation, and then you can describe more features with it. And so, commonly enough, we use the Gaussian kernel, which would be essentially like a smaller normal distribution. And so, moving forward, we can depict together what it would look like to have the histogram in the black lines, our kernel estimate with the red line, and then the true, potentially true distribution, and in this case, it's rather normal. And so earlier I described a little bit about the bin width and bandwidth, and in particular the bandwidth for the kernel. It does some smoothing, which would essentially mean that for a histogram, if we have one bin along the entire range, that means we count every single observation and stack it vertically, and you can't see any difference between certain intervals of that range. Now, if you have two bins, that means you essentially break it in half and you can see a step. Likewise, if you have more bins, you can describe more steps, and then you can actually derive a shape from the actual distribution. And so this is a key component to statistical visualization. Now, I'd like to point out that this isn't necessarily true kernel approximation, mainly because we have it going off right here, and that's not necessarily feasible. And so I would like to cover that this is a relatively big bin width. And so our smoothing shows almost no really good representation of the data insofar as we have these condensed areas where there's actually a decent amount more observations than there is around it. And so being able to describe those little bumps in our graph is actually valuable because it actually better represents what we found in our experiment, or better represents the actual true distribution that we're deriving our data from. And so this is then again shrinking our bandwidth, and so we get, as you can see, a more accurate depiction. There's more bumps, and that's essentially describing more condensed areas where we had observations. And likewise, this would be what would be a potentially reasonable approximation, because our bandwidth is not showing something that's over-smoothed or something that's under-smoothed. And now a good representation of what's under-smoothing then is this, where we put too much emphasis on each observation, essentially. And so here you can see that, well, it is very unlikely that you get a gap in the data, but here it's showing that there's so much emphasis around even there that, like, granted, there's no observation there. There's this huge bumps or modes, I guess you would say, and then tons of little anti-modes everywhere along this graph. And is it really a good representation of our distribution? Probably not. And so these are the two readings I'm doing, the books that I'm reading with Professor Minotti. And this source quotes essentially the first source. It's a very good presentation of it. And I guess these are the sources I used in the readings. And yeah, so my actual PowerPoint I had actually had acknowledgments on it. And so I'd like to thank Professor Minotti for giving his time essentially to teach me an uncommon topic in statistics, and the McNair program for affording me this opportunity. So.
So what type of applications are you using this lab application in the future?
I have not gotten that far. So far I'm just doing proof work of this. I didn't cover that today, mainly because it's, I guess it'd be harder to explain it, and because I'd have to assume more people's math background, and that's just not something you're supposed to do. So there are other applications, I guess. I can't really think of any in particular, but that's a realm I'd like to delve into in the future. So.
There's one example I could give you in geography. So we do remote sensing in geography, and common sensors, Landsat. That made like your first example. You shorten up the bandwidth. It's your bins. It'd be like hyperspectral imaging, where you have a lot more different bands, look at different features in more detail. That would probably fit into this type of application.
Yeah, definitely. Yeah. I actually
just an idea for you.
Oh yeah, that is pretty cool. Actually, this Professor Tarn Duong, he does it in biostatistics. And he represents tiny little organelles as little kernels, and so it's almost incredible to even imagine that there's a probability for each organelle being represented like that, and so there's a lot of weird applications because it's just really diverse. So. Anyway, yeah. I'd like to point out the PowerPoint was actually really nice, and I wouldn't have had to do any slide swapping and stuff like that. It's all right. It's just
This one was good too.
yeah. I prepped for that though, so that it would have been a little bit better too, because I wouldn't have been as nervous.
I'm sorry, that
No, it's all right.
was in translation. It got missed somewhere.
Okay.